Hey guys, welcome back to Create Code. Today we're doing another Brainstellar Quant puzzle. This one is called consecutive heads. It's a pretty classic probability problem in my opinion. It's of medium type. So you guys can pause and go over the problem once. So basically what we've been asked is pretty straightforward. We have to calculate the expected number of coin tosses required to get n consecutive heads. And it's denoted by E of n. So first of all, let's create a random variable, say x of n, which denotes the number of coin tosses required to get n consecutive heads. So this is x of n. Now, what we've been asked is obviously e of x of n, which is also denoted by e of n over here in the problem. Now, to go about this, basically we could try to take up values of n as 1, 2, 3, and you soon realize that these cases in themselves are pretty complicated to find out, and you don't really come anywhere near the general formula E of n. But there's one neat observation that you can make, that the value E of n is pretty closely related to the value of E of n minus 1. Try to think about this particular relationship. How could you calculate the value of E of n using E of n minus 1? And using this relationship, we could create a recurrence relation. So try to think about it. And another hint that I'd give you guys is that in this type of problem, as we saw in the previous problem, which was the innocent monkey, the scenario is going to reset, or the entire situation of the problem might reset at some particular stage in some of the cases that we're going to consider. And the trick that we have to use over there is that if the scenario resets, then we can use E of n again in the formula. So for example, if I'm calculating E of n and I'm trying to add up all the different cases, now if in one case the expected value is E of n, or this is basically the case where the entire scenario resets, then we can have the probability of the scenario resetting over here, and the value that it is multiplied by is E of n in itself. Right? This is the trick we used in the previous problem, and we're also going to use this trick again over here, because the situation of the problem is in some particular cases going to reset. Okay, so keep these 2 points in mind. One is the recurrence relation, second is the scenario resetting situation. Now this line over here basically explains everything about this solution. Note that if we already have n minus 1 heads, now don't worry about how we got to this point, right? And that is important to understand when we're thinking about recurrence relations, that our base case is n minus 1, right? So in this case, then if the probability of getting a head is 1 by 2 and the probability of getting a tail is 1 by 2, but if we get a head, then we get n consecutive heads and condition is satisfied. And if we get a tail, which is also a probability of 1 by 2, then if you try to think about it, the entire state been reset. Now think about it. If you get any number of heads, well, given that this is less than n, right, and then you get a tail. Now since all of the heads that we need are consecutive, this tail makes sure that from this point onwards we have to do the entire work again. We have to bring about n consecutive heads again. So basically this point onwards, the state is exactly identical to the state as it looked from this point onwards. So from this point onwards is the exact same as this point onwards, since we got a tail and the chain of consecutive n heads was broken, and so we need to get n consecutive heads again, right? So what this means is that E of n is equal to, now we're going to take both cases, and both cases have a probability of 1 by 2, right? So in the first case, we had E of n minus 1, which was the expected number of tosses we would need to get n minus 1 consecutive heads. Then we got a head. So this 1 by 2 denotes the case where we get a head. So I'm just adding one more coin toss because we need the next head. In the other case, we initially had E of n minus 1, as that was the expected number of tosses that we would require to get n minus 1 consecutive heads. Then we got a tail, so I'm also going to count that as plus 1. And then there was another value, which was, because the state was completely reset, then what is the expected number of more coin tosses that we're going to require? It's going to be E of n. This is the exact same concept as the previous problem we did. So this is the recurrence relation that has been formed. And this basically boils down to E of n is equal to twice of E of n minus 1 plus 2. Now this is the recurrence relation. And you could use this to calculate the expected number of coin tosses required to get n consecutive heads for n value equals to 1, equals to 2, equals to 3, and so on. Now this is the answer in the recurrence form. You could also calculate the explicit closed form, and for that you need to use a bit of math. So I'll just show you the Brainstellar solution. So this is the Brainstellar solution we discussed up to this point. Now, so basically what they've done is, since E of n is always greater than twice of E of n minus 1, this observation itself, well, obviously there's also another factor over here, but we're not focusing on that right now. So this part in itself shows that the function E of n is going to be exponential. Every time n increases by 1, E of n doubles, right? Because E of n is always twice as much as it was for one less value. So we could generalize this as E of n is c times 2 of n plus b. So basically where c and b are two constants. The way they took over c1 and c2, and they took different values of n, right? By plugging n is equal to 0, n is equal to 1, and getting the values of c1 and c2 and solving that, we get to this final value. So this is the final answer. E of n is equal to twice of n plus 1 minus 2. I hope you guys understood this approach, and thanks for watching.